Hi, I am Said Abulfaz, and this is the second video about optimization in neural networks. And in this video, I want to speak about gradient descent with momentum, and Nesterov gradient descent. As you can see, and as you remember in the previous video, I showed you the error surface of ResNet 56 without using a skip connection. You can see here. This is the okay. This is the loss function, error function of ResNet 56 neural network deep learning model without using a skip connection. ResNet is one of the most famous algorithms in computer vision that proposed by K and its team members. As you can see here, in this loss function of ResNet, you can see here there are many local minima here, like this, and here, and here. But something that we want to reach is here. We want the global minima. We want to reach this point here. That is the global minimum, and here we have the minimum loss value of the loss function. But as you can see here, if you, for example, start your training your neural network from here, from this point, you may stuck in here in a local minima, and I make it okay. Maybe you're stuck here in local minimum, and if you start, for example, from here, okay. You start from here, okay. And if you start from here, you go here, and then you will start here in another local minimum. But we should have good optimization methods, and we should have some rules in optimization method in neural network weight initialization to reach the global minima here, where the loss function is minimum. And this is the concept that we want to speak about here. And as you can see here, this is another loss function in a little easier way. You can see here, this is a loss function here. Maybe you start turning your network, and you start the initial base from here, and you may get here. This is a global minimum. But maybe you start your initial weight from here, and you stuck here. Means that you reach to local minimum, not global minimum. This is not suitable for training neural network. Or sometimes you start from here to train your neural networks, and go here, step by step, go here, then we'll reach here. We should have a method. We should have a method that we can here, when we reach here, we could step forward and pass here the global minimum, and pass from global minimum here. From here, we pass the global minimum, and then continue our training to reach here, that is the global minimum. This is the concept that we want to speak. And in addition, we have saddle points sometimes in loss function. Saddle points are points like this. You can see here, this is a saddle point. Means that this is local, this is a minimum for here, for this curve. This is not a very visible curve. With this color, use another color. Okay, maybe this is a minimum for this curve here, but a maximum. This is a maximum for this curve, here, and from here and until the end, until here. This is the saddle point. Means that for one curve in your loss function, in your loss chart here, this is a loss function. as you can see it from one view, from here this is minimum, and another view this is maximum, and we want to pass this saddle points to, this is saddle points, we call this saddle points. It means for here it's minima, and for here, if we see from here, this is the maximum. We should have some optimization methods that can, there are some optimization methods that help us to tackle this problem. Okay, as you can see here in another example, we start turning the neural network from here, we go here, here, and as you can see here, this is the steepest from this point, means that the steepest means gradient is more, and as you can see here, the step is larger, and we get here, and this is this is a steepest again, very steep again, and a larger gradient, but this larger gradients lead to reaching this point, and means that we lost global minimum. And after this point we go here and we go here, means divergence. We see divergence here. We can't reach global minima here. We pass global minima, we can't reach to the global minimum. Okay, and this is the problem that we have in vanilla gradient descent, in standard way of gradient descent that we see until now. This is the problem with standard vanilla gradient descent. We can have a trick to tackle this problem, and we use momentum here. This is the mathematical formula for momentum. I explained it. Okay, don't be scared from this formula. That's very easy. Okay, this formula says that we have the standard formula for updating weights in gradient descent is this: t theta t new means theta t old equal to theta t old minus learning rate alpha to the multiple to the gradient of loss function and the gradient of weight. For example, here the weight theta. This is the standard gradient method that we speak about in the previous video. But as you can see here, we use a term momentum here. This is standard. This is this sentence and this sentence are the same, but another term is added here, means this. And as you can see here, this formula says that t equal to theta minus this. Okay, minus and this formula. Okay, as you see here, and a term, this term is this term that I said with a star. This is the star term, a star here, and this is a star here. Okay, this term and this term is equal. Okay, As you can see here, this formula is this formula, but we added a simple term here. This term is added, or this term is added, and this is an easy term. What this means? This means that for each step, for example, we start from here, or we should calculate a speed vector 2. What this means? Okay, I explain it. Here, as you can see, we have the gradient here, and the speed is here, and here we have a this is the gradient vector, and this is the speed vector. Means that we have sum of these two vectors, and we have a larger change here. We have a larger change because gradient is gradient is in this way, and minus of gradient is this way. But here we added speed. This is the speed of vector. The means the direction that we came here, in which direction we can get to this point, and this is the speed direction. And we have the sum of two vectors, and we get a larger vector here. And for this vector we get a larger vector here too, because here the gradient is in this direction and speed is in this direction too. But what we have here, this is a good question. Here we have this gradient function here. This is the gradient function here, but the direction that we went from here to here, we went from this point to this point, is this. Okay, better we have this direction. Means that because until here we go in this direction. This is the direction that we are going, and this is the direction of gradient. And as you can see here, we have two vectors, this vector and this vector, and we should calculate the sum of two vectors. Sum of these two vectors is this. Sum of these two vectors is, and this is the sum of these two vectors. And this means that it goes here for t. It goes here. Means that the next, I write it in a cleaner way, for this direction, we have this gradient and we have this speed vector, and we have two vectors. Sum of these two vectors is this like this, and we go to this point. Okay, and means that we have the chance to reach the global minima. Here is the global minima, and we using for momentum lead to a better solution. We instead of going to here, I go to here and reach this here, and in next step we go here and here, and you can here see that after some oscillation we can get the global minima that is here. Okay, means that it's a very good solution. And in addition, okay, means that, okay, to explain it better, we have two amazing concepts here. The first and most important one was that here the direction of speed is here because we are going in this direction, and here the speed of the direction of gradient is here, and this is the sum of these vectors. Means that we reach here, and after some oscillation we reach to the global minima. Okay, after some oscillation we reach to the global minima. Okay, this is one way. This is one amazing point about this. Another amazing point is that after going one way, here it is the gradient, this is the gradient vector, and this is the direction vector. Means that here we have some of these two vectors, means larger speed, we can reach to this point here faster, and because we go instead of here we go here, because this is some of two vectors, and we have larger step here, and in next step here we have this gradient and direction, means we have larger step here, and after that we have this gradient and this direction here, means that we have larger space too, means that we can reach faster here in the starting points, in the points that are flat, we have larger step, and we can reach to the minimum to the this value faster. As you can see here, we have in the global minimum we have this, but after this you can see larger steps in direction to get the global minimum. And in addition, it can reach to the global minimum with some oscillation. Okay, this is very good idea. Yeah, you can see here global minimum oscillates around minimum before eventually reaching it, and it is faster than vanilla gradient. After 100 iterations, momentum based gradient has error of this, and whereas vanilla gradient is this. You can see here how fast this momentum based gradient is. But we can use Nesterov momentum to make this oscillations around this global minimum, to make these oscillations around global minimum very less. Okay, you can see here this is the Nesterov momentum gradient. This Nesterov momentum gradient was first introduced by Nesterov in 1983, and he introduced that, but usually scientists didn't use that. But in 2013, Ilya Sutskever, who is one of the famous scientists in the deep learning in this area, one of the writers of AlexNet papers, and you can see many good papers is created by this Ilya Sutskever. He introduced that Nesterov momentum in 2013, and after that, using this Nesterov momentum get more popular. It was invented before, but by Nesterov, but it got famous after 2013 by reintroducing that by Ilya Sutskever. This is the formula of Nesterov momentum. You can see a very easy formula here. Nesterov momentum has an easy idea in his background. Says that we have this before, we have this before, we have this before, we have this before. Another, only one term is added to the momentum based gradient is this. What this means? This means that when you got here, when you reach here, first go one step forward here. Okay, another, I should use another color for better explaining. Okay, this color is good. It says that first, when you reach here, first go a little forward. This term says that first go a little forward, then get gradient and momentum, and like that get after reaching here, use the gradient and use the speed function, and use this sum of these two vectors to get the next point. You can see here going one step forward and then using gradient, sum of gradient and vector functions, speed function, means that we can have less oscillations here. We can have less oscillations because instead of oscillating from this point, we're oscillating from this point. It means less oscillation here, and in each steps this oscillation is less too, and it speed the it has a very good effect on the speed of convergence in the gradient, in the momentum based gradient. As something that very important you can see here is that usually we use 0.09 for this momentum here and this speeds, and you can see here this speed will be get it in from this is dependent on one step before, and this dependent to the one step before, and you can see here, for example, this Vt dependent to, for example, if this then the momentum is 0.09, this dependent to the one step before, and this one step before means it dependent on one step before this step and go there. Means that, for example, here Vt is Vt dependent to 0.09, Vt one step before, the speed of one step before, with t minus 1, and Vt and 0.81 to a step behind, and so on. Means that because this is the multiple of these two, means that in each step this is more dependent to the previous step, and this is the something that we speak about today. You can see here for the convex loss function that in real world scenarios you never send the converse loss function vanilla gradient descent is very good, is amazing, but for non-convex situations or non-convex loss function, you can see your non-convex loss functions, momentum based Nesterov momentum based gradient is amazing. You can see here, this is convex loss functions, and here non-convex loss function, and you can see here SGD using standard momentum, and here this column is Nesterov Momentum SGD. You can see here Nesterov Momentum SGD has less oscillation to reach the global minimum, and momentum, standard momentum here has some oscillation to get the global minimum, and SGD never reached the global minimum. Here is the global minimum. SGD standard vanilla SGD never reached the global minimum in non-convex optimizations. An amazing figure that shows everything that I said it to you, and you can see here this is the PyTorch code. We do some, I record video to do many amazing projects to you, but in here, after speaking about the Nesterov momentum, I said that this is the PyTorch code for using momentum and momentum gradient, SG gradient, momentum SGD, vanilla SGD, and Nesterov Momentum SGD. Momentum SGD. You can see here, if you set it to, if you set the momentum, you use momentum SGD, and if you set the Nesterov to true, you use this Nesterov SGD. You can see here using Nesterov Momentum SGD was very amazing. We can reach to the global minimum, and it's better than standard gradient descent. But there are a question here. We have an issue here using a standard learning rate. As you can see, a slow learning rate means that a slower moving to the global minimum, and larger learning rate, for example, larger learning rate here, for example, larger learning rate means goes here, then goes here, then goes here, then goes here, means that larger learning rate sometimes may lead to the divergence. Having a good learning rate is a question here. We can use some methods like rich search, like random search. I record video about that and upload it to the YouTube. But is there another way, another method to customize the learning rate for better reaching the global minimum? As you can see here, having a suitable learning rate is important. Can we have some methods to have customized learning rate and better learning rate for each rate to reach the global minimum? This is the question that we want to answer it in my next video. Have a nice time. Bye bye. If you didn't subscribe to this channel, and if you see that, if you think that these videos are amazing for you and are suitable for you, please subscribe. Have a nice time. Bye bye.